Hello and welcome back to the channel. In this video, we're going to do a beam deflection problem on a beam that has an overhanging section. The problem involves a wide flange, 10 by 33 I-beam that has a distributed load from it was the left-hand section all the way to the roller. It has a magnitude of 400 pounds per feet. And there's also a point load or concentrated load of 3.5 kips at the very end. Now this I-beam is made of A 913 steel, and we want to determine what is the maximum deflection at the right hand section of the beam, this point over here. If you can imagine, right, when we apply this distributed load, it's going to make the beam deflect downward, so then it's going to curve up, right? So the distributed load will cause a positive, or I should say an upward deflection at this end of the beam, while the concentrated load pushes down. So which one will win? We'll figure it out. All right, so let me move over to OneNote so we can work out this problem. All right, so here I'm at OneNote, so we can go ahead and solve for the deflections of the beam. Now, what we're gonna do here is we're gonna use a method of superposition, which involves looking at the different types of the loading that is acting on the beam. So here, one type of loading that is acting on the beam is a distributed load. And we can see that, so if I just isolate the case for the distributed load, we can see that it's being applied between the two supports. The distributed load is acting down. So if we draw the deflection curve of the beam, we would expect to be concave up over here between the supports. And then after the supports, there's no loading acting on. So we have basically just a straight line over here. And what we can see is that at the right-handed support, that deflection is going to be upward. Now, if we look at the case for the point load, 3.5 kips over here, which I drew on this right-hand side. So that force is concentrated down, right? So that right end of the beam is going to be deflected downward and it's going to kind of curve up like that. It's going to be concave downwards. And so the deflection is downward. So we're going to see here already that there's going to be an upward deflection from the distributed load and a downward deflection from the point load. Now, what is going to be the deflection of the beam? Well, it depends on the magnitude, the number, how big each one of those are. We already know they're acting in opposite directions, so we're going to take the difference, and whoever one is bigger, then it's going to indicate if the deflection is up or down. Now, before we start crunching numbers, we're going to need two properties of the beam. One of them is the elastic modulus, and that's a function, or it depends on what material the beam is made up of. In this case, it's A913. So what we do is we go to the equation booklet and we look at the properties of steel. And we're looking, again, remember the specifically modulus of elasticity here is in units of 10 to the 3 KSI, or you can think of taking the number below and multiplying times 10 to the 6 to have it in units of PSI. Anyways, if we scroll down to A913, we see that the elastic modulus is 29. So let's go ahead and write that down. Elastic modulus, I'm going to put it up here, is 29 times 10 to the 6 PSI. Now the other property that we're going to need is the moment of inertia of the beam. That's a function of the cross-sectional geometry of the beam. Now here they don't give us a picture of the cross-section, but they do tell us that it's a W10 by 33, which means it's a wide flange I-beam. So if we can find the moment of inertia, it's going to be tabulated in our equation booklet. So we're just going to scroll down and we're going to look for the I-beam sections. Here we go. I-beam sections, W. Shapes would mean wide flange shapes. And we're looking for the W10 by 33. So we scroll down. This is W20s, 18s, 14s, W12, W10, and here I have it boxed in, right? So this is all the kind of properties for that cross section. What we want is the moment of inertia, which is I, and here we have two to pick one, Ix and Iy. So which one do you pick? Well, it depends, right? In this case, the loading is going to be up and down. So the neutral axis is going to be the XX. So we need the moment of inertia about the XX axis, or the IX, which is 171. And the units are inches to the fourth. So 171 inches to the fourth. Now, another thing that I would like to do right now, before I start plugging in values into the different equations, is to have everything in base units. So you can see here elastic modulus in pounds per square inch, moment of inertia in inches squared. But when we look at the beam, we have lengths in units of feet. So I want to go ahead and convert that to units of inches. So first 10 feet times 12 inches, right, is going to give me 120 inches. So 120 inches right there. And then the other one, 6 feet times 12, going to be 72. Oops, sorry. So this is 72 inches. Now the other thing I like to convert is the units for the different types of loads. This 3.5 kips, I don't like kips, right? So I'm just gonna write it as 3,500 pounds. And then the other one, the distributed load, it says 400 pounds per foot, but we're gonna be working in units of inches, right? So we wanna convert it to units of inches. So we know that 1 foot is 12 inches. So we go ahead and type 400 divided by 12. We get 100 divided by 3, or 33.3333 pounds per inch now. And so this way, when we type it in the equations, we have everything in pounds and inches. And we don't have to worry about converting each the dimensions again over and over again. All right, so we have the two cases. Let me go ahead and do first the case for the concentrated load over here. So the case is a concentrated load. So let's look at the equation booklet. Oops, wrong menu, equation booklet. And let's start looking for an overhung beam. So here we have overhanging beam. And we have the case where there's a concentrated moment at the end. And this one is a concentrated force. This is the case that we have. If I scroll up, we see that the next ones are cantilever. So that doesn't apply. Right, so we have overhanging beam, point load at the very end, and we are looking at the deflections. Remember, the first column over here gives you the slope and angles of radiance, and then next over here we have some equations for the deflection. Right, D is the deflection of the beam. And here we can see that they give us two equations. The first one has limits of x between 0 and a, and the other one is limits for z between 0 and b. So what is x and what is c? So always look at the figure over here, and we see that x is the distance from the left-hand support going towards the right, and it has a maximum of little a, where little a is the span between the supports. So again, the first equation over here covers for the deflection at any point between the supports. The second equation over here, in terms of z, it's a function of z. Z here starts at the right support and extends towards the end of the overhanging portion, right? So we want the deflection anywhere between the last support and the tip of the beam. We're going to use the second equation. And so this is the one that we'll need to use. Let me go ahead and just take a copy of this one. Actually, let me copy the whole thing, probably easier this way. I'll go to the OneNote. I'm going to put it here underneath. There we go. That way it's a little bit neater. Again, the equation that we're going to use is going to be this one right here. So let's just go ahead and figure out what the deflection is. So deflection from a concentrated load, and in this case B, is equal to P times Z divided by 6 AI. So what is P, you ask? Well, P is the concentrated load. Remember, the concentrated load is 3,500 pounds. LB. Next is little z. And again, remember, little z is the distance from the right-handed support towards the end of the load. So in that case, z since we want the deflection right at the very end, right, Z equals 72 inches here. So times 72 inches, that's divided by the constant 6. E is the elastic modulus, we said was 29 times 10 to the 6 pounds per square inch, times I, which was, let's check again, 171 inches to the 4th power, and then times this here in in parentheses. In parentheses, we have the number 2. Next is little a, and where little a is the distance between the supports. So that's 120 inches. And next is b, and b is the distance of the overhang portion. So that one was 72 inches. And then plus 3 times b, which is 72 inches, times z, which is 72 inches, minus z squared, which is 72 inches squared. Now, if you notice, I started putting inches and inches, and then I stopped, and we can see here, right, each of these quantities, anything that's in here is going to have units of inches squared. Anyway, so we type this on the calculator. We get 0.2342 inches. So that's the how much. Next, we also need to keep track of what's going to be the direction. And we can see from the deflection curve here, the elastic curve of the beam, right? The deflection is going to be downward. So I'm going to put a little down arrow right here. So that's from the concentrated load. We know how much for this guy. Next, we want to figure out what's going to happen with the distributed load. So to do that, again, we go to the equation booklet. Let me get rid of this. Right, we're still working with the overhanging beam. But again, we have the equations just for a point load and a moment over here. And there's nothing else for overhanging. If I go to the next page, we're on the I-beams. If I go a page before, it's cantilever beam. And so what do we do in this case where what we have is a distributed load in between the supports, but we don't have an equation for that case. So what do we do next? So what we're going to do instead is, well, since we don't have the overhanging portion, let's look for if we have for in between the supports, right? So in the between the supports, that would be considered, it's a pin and a roller, a simply supported beam. So do we have equations for simply supported beam? Let's scroll. This is cantilever, so that's not good. Cantilever beam, not good. Simply supported. Here we have a distributed load that does not cover the whole spans. Remember here, R1 and R2 are the reaction forces, so they indicate where the supports are. So here we go. Here we have a simply supported beam, right? Distributed load acts between the two supports. So this kind of looks at what we have, but what our problem has is that the beam extends over here. So how do we deal with that? And the answer is simple, right? We don't have an elastic curve for a portion that extends past the beam, but what we do have is we do have a slope over here. And so what we can do, look at this angle here, theta max, which they're calling W times L cubed by 24 EI. What we can do is we can exploit this slope over here. So let me put it over here. So we can exploit this angle theta. So that angle theta, because that angle theta is going to be the same one as that angle theta. See? So if we know the slope, and because there's no other external loading here up and down in the beam past the support, there's nothing stimulating the beam. So the beam is just going to be a straight line over here. So we can form a little right triangle right there. And with the use of the angle and some geometry, we're going to be able to find what's going to be the deflection over here in this upward direction. All right, so first let's find what the angle is. So I'm going to go to the equation booklet and copy down the equation for the angle. Here we go. I'm going to put it below, right there. And so let's solve for what theta is, right? So theta is distributed load times L cubed divided by 24 EI. So first, W is the magnitude of distributed load, which in our case is going to be 33.333 pound inches. Remember, we converted to pound inches. So 33.333 is in units and pounds per inch. Next, we're gonna multiply times L. Oops, sorry, the keyboard. We're gonna multiply times L. But if you notice here, right, this equation for the angle is based on this figure. So here L is just the span between the supports, which on our original problem is 120 inches. So we're gonna set L equal to 120 inches. And yes, I know that the beam is more than 120 inches long. It's overhanging. But again, this equation, right, this equation here is for that figure. And so we have to pick L as the number in between the supports. And remember, that number gets to the cube power divided by the constant 24 times E, which is 29 times 10 to the 6 pound per square inches, times I, which was 171 inches over here. To the fourth. All right, so if we put all of this in the calculator, what we get is 4.8396 times 10 to the minus 4. And if you go ahead and check the units for this equation, you're going to see that it's unitless, which means that that angle is in radians. We can also take that angle and we can multiply it times 180 degrees divided by pi radians to cancel the radians, and we can figure out the degree equivalent of that angle, which turns out to be roughly 0.02773, and this would be degrees, right? But that is that angle. How are we going to use it to solve for the deflection, you ask? Well, remember, here's our original problem. Here's one support. Here's the other support. The deflection curve, this is from the distributed load, right? So we know, just like in this case, that is going to go kind of down, concave up, and then up. And then when it's past the support, there's nothing bending the beam up or down, right? Because there's no other external loads. So from that point onwards, we have essentially a straight line. What we know now is this angle theta. Again, this one, which is the same as that one, that's the angle theta. And what we want to find out is what is this deflection here, right? Again, so I have a right triangle. And what I know is I know an angle. And I also know, for example, this dimension. This dimension was 72 inches, right? And so I can use that to figure out this opposite end, right? So if I write tangent of theta is equal to the opposite divided by the adjacent, right? The adjacent being this quantity over here, which is 72. So we can figure out what for this opposite side. So therefore, opposite side equals the adjacent, which is 72 inches, times the tangent of theta, which is 0.02773 degrees. So we type this in the calculator, we get that that opposite distance is 0.03485, and the units are inches, right, from that unit right there. So that's how much it deflects upwards. Again, we can use this one. We can assume that the adjacent here, that distance is still 72 inches. Because of that angle, it's a very small angle. Remember the small angle approximation, so we can approximate this opposite one just as adjacent times the tangent of the angle. Anyway, so if you recall what's going on, right? This one is going up 0.03485, right? So it's going up 0.03485 inches up. The other end, that quantity was 0.2342, 0.2342 inches, and that's downward, right? We can see that that number is much, much bigger. They're acting in opposite directions, so we're going to have to take the difference. So we're going to take 0.2342 minus 0.03485, and the number that we get is 0.1994 inches, right? Because this number is bigger, right? That direction wins, so we can say that the deflection at the right hand is going to be almost 0.2 inches in the down direction. All right, so we ran the numbers, and on this white flange beam, and this 400-pound per feet distributed load and 3.5 concentrated load at the end of the right hand section of the beam ends up producing a 0.1994 inches downward deflections over here at the right end of the beam. All right, so hopefully you found that example useful, where we went ahead and figured out the deflections in overhanging beams with the help of using the slope at the ends of the beams to figure out what happens past the supports. Remember, you can always use that trick whenever you want to figure out what's happening past the supports of the beam. So there we go. Hopefully you enjoyed the video, found it useful. We'll see you in the next one.